In this presentation, I am going to explain equivalent drive parameters of electric drive systems. What are the equivalent moment of inertia and load torque calculations? Coming to the equivalent values of drive parameters, that is, equivalent values means one is the load torque TL, second is the moment of inertia J, capital J. What is the equivalent load torque and what is the equivalent moment of inertia? In different cases, like two cases are we are considering. One we call it as different types of motions are, as you know, that one is a rotational motion, second is called a linear or translational motion. Now let us first consider a load with rotational motion. Load with rotational motion can be represented by this diagram like this one: motor and one load that is directly coupled to the motor, that is TL naught is the load torque which is directly coupled to the motor, and the total moment of inertia is represented as J naught. Now this total, again, that is connected, this motor is connected to another load through a gear reducing system, or it's a gear ratio with speed reducing using the gears. That gear ratio is equal to, this is a n number of turns, and here it is equal to number of turns equal to n1, or n by n1 is represented as the ratio a1, that is the gear tooth ratio is equal to a1. That gear is connected to the second load, and that is having a moment of inertia of J1, and that is rotating with a angular velocity of omega m1. This is omega m1, this is omega m, and this ratio n by n1 is given by omega m1 divided by omega m, that is equal to called gear tooth ratio. J naught is the moment of inertia of motor and load directly coupled to the shaft. That is, this is the J naught. It is the motor plus the load directly coupled to the motor, that is equal to J naught. If the losses of the transmissions are neglected, since the kinetic energy remains unchanged, half J omega m square, that is where J is the equivalent moment of inertia, half J omega m square equal to half J naught omega m square plus half J1 into omega m1 square, where J1 is the moment of inertia of this load. Therefore, equating the kinetic energy of these two kinetic energy, that is equated to half J omega m square, where J is called the equivalent moment of inertia. Continuing the equivalent values of drive parameters, already we have seen the equation: half J omega m square equal to half J naught omega m square plus half J1 omega m1 square, that is equating the kinetic energy, where n by n1 equal to omega m1 by omega m is called the a1, which is called gear tooth ratio, or omega m1 equal to a1 times omega m. Omega m is the angular speed or velocity of this shaft here, and here this opposite to that one, that is the angular speed equal to omega m1. Always will be opposite. This is the clockwise. This is here. Torque will be opposite here. This is motor torque, and the load torque will be opposite. And this is the speed omega m1, and this is the speed omega m0. Therefore, omega m1 equal to a1 times omega m0. Substituting for omega m1 in the equation 1 here, we'll be getting half J omega m square equal to half J naught omega m square plus half J1 a1 square omega m square. Therefore, omega m square gets cancelled, half and half also gets cancelled, half and omega m cancels, or J equal to J naught plus a1 square J1. This is the equivalent moment of inertia J equal to this moment of inertia J naught plus a1 square, the gear tooth ratio square, into J1, moment of inertia of this load. This is the equivalent value of the moment of inertia. Next one, we have to find out what is the equivalent load torque, TL. To find out the equivalent load torque, we are equating the power. Power at the load and motors must be same. Or we are assuming that transmission efficiency is equal to eta 1. Transmission efficiency equal to eta 1. Now, since the power at the load and the motor must be the same, the equivalent load torque is given by, that is equivalent load torque TL into omega m equal to, what is the load torque of this one? Load torque of which is connected directly to that one, TL0 into omega m, that is this power at this, plus what is the power at this point? That is, it is equal to TL1 into omega m1, that is the power, divided by this efficiency. That is the efficiency of the transmission efficiency of the gear equal to eta 1 divided by eta 1. We are equating the power. Therefore, that is equal to, this is equal to TL0 into omega m plus TL1 into omega m1 is replaced by A1 omega m divided by eta 1. Omega m gets cancelled, or the equivalent load torque equal to TL0 plus TL1 A1 divided by eta 1. Therefore, this is the equivalent load torque and this is the equivalent moment of inertia in the case of a rotational load with a rotational motion. In the previous slide, we have considered only one load which is connected through the gear system. Now, in addition to one load, in addition to the directly load connected coupled to the motor with the inertia J0, if there are m other loads with a moment of inertia J1, J2, etc. Jm, and gear ratio equal to A1, A2, etc. Am, and transmission efficiency eta 1, eta 2, etc. Eta m, actually it's equal to eta m, equivalent moment of inertia is given by J0 plus A1 square J1 plus A2 square J2 plus etc. A3 square J3 etc. Am square Jm. This is the equivalent value of the moment of inertia if there are m if the m loads are there connected. And in this case, the equivalent torque is given by TL is equal to TL0 plus TL1 A1 divided by eta 1 plus TL2 A2 divided by eta 2 plus etc. TLM AM divided by eta m. Therefore, this is the equivalent moment of inertia and this is the equivalent load torque if there are m loads with moment of inertia J1, J2, etc. and gear ratio A1, A2, etc. Am, and transmission efficiency eta 1, eta 2, etc. eta m. Continuing the equivalent values of drag parameters, equivalent value of the load torque and the moment of inertia. Previously, we are considered as a rotational motion, load with a rotational motion. Now we are going to consider load with linear motion or translational motion. In that case, one of the load is directly coupled as in the case of previously, that is having a load torque of TL0 and the total moment of inertia equal to J0. And the second one is connected through a, that is rotational to the linear transmission is this, converting a rotation to linear. And that this is another second load which having a mass capital M and force equal to F1 and the velocity equal to V1. This is a linear movement. It's a moving up and down. It's a linear movement and this is the rotational movement. Now, a motor drive with two loads. One is directly coupled to the shaft, that is this load which is directly coupled to the shaft. Second one is coupled through a transmission system converting the rotational motion into a linear motion. This is the system which converts the rotational to the linear motion. This is the second load that is connected. Now, J0 is the moment of inertia of the combined motor and load directly coupled to it. That is motor plus the load which is directly coupled to this one. The total moment of inertia is given by J0. And TL0 is the torque of the load directly coupled. That is this torque TL0 is the load torque which is directly coupled to the motor. Mass, force and velocity of the load with a translation motion, that is M1 is the mass, F1 is the force, V1 is the velocity, which is the linear motion, it is a translation motion. If transmission losses are neglected, the kinetic energy due to the equivalent moment of inertia J must be same as the sum of the kinetic energy of the various moving parts. Now equating that one, half J omega m square, this is the equivalent moment of inertia equal to J. Half J omega m square equal to half J naught omega m square, J naught is the moment of inertia of this one, plus half m1 into v1 square, half mv square, half m1 into v1 square. This is the equating the kinetic energy. Continuing the load with the load with a translational motion, linear motion. And previously we have seen equating the kinetic energy, half J omega m square equal to half J naught omega m square plus half m1 v1 square. Now here dividing omega m square in both left side and right side, equivalent moment of inertia J can be obtained as J naught plus m1 into v1 divided by omega m whole square. This is the equivalent moment of inertia in this case. And the power at the motor and the load should be same. The power should be, you can equate the power. And equating the power is nothing but torque into omega. That's called the power. Therefore, the load torque into omega m, where load torque is the equivalent load torque. And that's equal to TL naught into omega m. That is TL naught into omega m plus power of this side. Power is given by F1 into V1. That divided by the transmission efficiency of eta 1, F1 V1 divided by eta 1. We are equating the power, the force into velocity. That is the power divided by eta 1. Then equivalent load torque. From this equation, if you calculate the load torque, omega m, you divide omega m here. Load torque is given by TL is equal to TL naught, that is the load torque of the load directly coupled to motor, TL naught plus F1 divided by eta 1 into V1 divided by omega m. Therefore, this is the equivalent load torque and this is the equivalent moment of inertia in case of load with translational motion. Continuing the translational motion, load with a translational motion. If in addition to one load directly coupled to the motor shaft, if there are m other loads with translational motion with a velocity v1, v2, v3, etc. vm and with a mass m1, m2, etc. mm, then equivalent moment of inertia. This is a generalized equation for the moment of inertia and the load torque. J equal to J naught plus m1 into v1 divided by omega m whole square plus m2 into v2 divided by omega m whole square plus etc. mm into Vm divided by omega m whole square. This is the equivalent moment of inertia. Similarly, the equivalent load torque TL is given by TL naught plus F1 divided by eta 1 into V1 divided by omega m plus F2 divided by eta 2 into V2 divided by omega m plus etc. Fm divided by eta m into Vm divided by omega m. Therefore, this is the equivalent load torque and this is the equivalent moment of inertia in case we are connecting m loads, translation loads with a velocities v1 to vm and masses m1 to mm. Now coming to a problem, a motor drives two loads. One has rotational motion and it is coupled to the motor through a reduction gear with gear ratio A equal to 0.1 and transmission efficiency 90%. That is represented this one. Second, the load has a moment of inertia of 10 kg per meter square, 10 kg meter square, and the load torque of 10 Newton meter. Other load has a translational motion, that is the second one. This has a translational motion and consists of 1000 kilogram weight to be lifted up at a uniform speed of 1.8 meter per second. And coupling between the load and the motor has an efficiency of 85% and motor has an inertia of 0.2 kilogram meter square and runs at a constant speed of 1120 rpm. Determine the equivalent moment of inertia referred to the motor shaft and the power developed by the motor. For equivalent moment of inertia and equivalent torque as well as the power you have to calculate. And this is the diagram batch on. One load is connected through a gear. This is a rotational motion is there, and here this is the linear motion. Coming to this one, equivalent moment of inertia is to be calculated. For that problem, J naught is given 0.2 kilogram meter square, gear ratio is given 0.1, and J1, that is the moment of inertia of the load, 10 kilogram, and the speed is also V1 is given, and the RPM is given 1420 RPM, and the mass M1 is given as 1000 kilograms. These are the data given. And here you have to calculate what is the omega m, angular velocity, which is nothing but 2 pi n divided by 60. 2 into pi into 1420 divided by 60, 148.7 radians per second. This is the angular velocity omega m. Now coming to this one, what is the equivalent moment of inertia? Equivalent moment of inertia, J equal to J naught plus A1 square J1 plus M1 into V1 divided by omega m whole square, because we have a linear motion plus rotational motion. This will be contributing due to the rotational motion, and this is due to the linear motion. Therefore, the combinedly, if you take J equal to J naught plus A1 square J1 plus M1 V1 divided by omega m whole square. Now substituting that one here, J naught A1 J1 M1 V1 and omega m, this equation, you will be getting it is equal to 0.4 kilogram meter square. That is the moment of inertia, equivalent moment of inertia. Now second part, equivalent load torque you have to calculate, then only you can calculate the power. Therefore, equivalent load torque is given by TL is equal to A1 TL0 divided by eta 1 plus F1 divided by eta 1 into V1 divided by omega m. Therefore, this is due to the rotational motion, and this is due to the linear motion, say moving up. This is a linear motion. The total load torque is equal to sum of these two, and if you substitute each one here for TL0, A1, F1, eta 1, V1 and omega m here, it will be getting 117.53 Newton meter. Therefore, this is the equivalent load torque, and this is the equivalent moment of inertia. Now, the power developed by the motor that is equal to the product of load torque into omega m. So substituting that one, you'll be getting it is equal to 17.476 kilowatt.